Hello, my name is Carlos Curran. I'm a senior software development engineer with Amazon Web Services, working on scripting in the Open3D engine. I'm going to give a rapid overview of the entire ScriptCanvas pipeline using the simplest example that still involves all of the steps. In O3DE, the goal for ScriptCanvas is to make the whole system and each component extendable and easily reusable in multiple contexts. The example context in this presentation is creating gameplay or simulation logic using the entity component system. Gameplay logic is the first and most developed use case for ScriptCanvas and has already been used in ship titles. At each stage of the pipeline, I'll discuss options for modifying and extending the stage for other contexts and use cases. Let's start with a quick overview to provide some clarity for the times when I refer to later steps while describing the earlier steps in more detail. We start at the editor, where a user translates their thought for gameplay into a visual representation that both humans and computers can understand. But the focus is on making the functionality as clear and easy as possible for humans to reason about. The next step is a parser, which converts an error-free ScriptCanvas graphs to an abstract code model and builder requirements. Two different systems make use of the abstract code model. The first one is translation, which converts it into the target runtime implementation. In the gameplay case, it translates the graph into Lua, which can be executed immediately. The other system that consumes the abstract code model is the prefab system, which works with the component entity system to build the ScriptCanvas runtime component. Finally, at runtime, the ScriptCanvas runtime component will initialize and activate when its entity does, and will execute the actual logic the user wrote in their graph way back in the first step. So now let's dig into the pipeline for more detail. Starting with the editor, where the user writes their intentions for gameplay logic. ScriptCanvas language allows the users to create logic by creating directed acyclic graphs. The nodes in the graph primarily define transformations on data, but frequently also define flow of control logic and useful syntactical sugar for constructs of the O3DE API, like ebuses and ebus handling, for example. The edges in the graph define the flow of data and the general flow of control. The roots of the graphs explicitly define functions that can be used in ScriptCanvas graphs, or implicitly define functions that will be called by the hosting instance of O3DE at runtime. There are three ways the developer can most quickly extend ScriptCanvas with full stack support without modifying ScriptCanvas system code at all. Firstly, by simply reflecting new methods to the behavior contexts. This reflection of the C++ runtime is reflected to all scripting contexts in O3DE and is automatically consumed by ScriptCanvas throughout the entire required pipeline. There's another opportunity here for modifying ScriptCanvas by making changes to the editor node palette. By restricting the available nodes from behavior context, it effectively becomes possible to make a domain-specific language by selecting only methods and behavior contexts tagged with certain attributes. Developers can also add new methods via the node function generic systems and libraries, though they should note, this method is intended for ScriptCanvas only functionality. They should not assume these functions will be easily available in other scripting contexts. Another method to modify the full stack, while still not touching any of the ScriptCanvas pipeline code, is through the use of notables. Notables are intended to allow users to write C++ objects almost as they normally would, and ScriptCanvas will turn the developer's specified interface into a node that can be used in ScriptCanvas, with the appropriate slots representing execution and input and output data. Because any of these objects themselves can introduce any number of entry points into the graph, they effectively can define domain-specific languages in and of themselves, even to the point of turning ScriptCanvas into a pure state machine editor or other unique form of describing execution. Adding nodes that do not fit any of the above or that do not follow the grammar patterns established by previous nodes is possible, but when it happens, the developer must modify the backend, and this will start with the parser. Parsing is where ScriptCanvas graphs are converted into an abstract code model and builder requirements, or possibly an error report. The purpose of this step is to provide a hard break between the front end of a visual programming language from all of the back end of creating functionality or an implementation. The abstract code model protects the back end from implementation or visual changes to the language. This allows us to continue to make the front end more visually appealing and more visually expressive, more easy to use, without having to modify the rest of the pipeline. The parser will check every node, variable, and connection in the graph for errors. It will generate every route of execution and every possible execution path through the graph that the user defined. It will perform some optimizations, for example, culling unused variables. After the graph is parsed, no part of the backend ever needs to know or should that the abstract code model was the result of parsing a ScriptCanvas graph. In general, extending the parser involves making custom modifications to handle your new visual situation. When we get to the translation step, this is where abstract code model is converted into whatever implementation of the original graph is deemed appropriate. Currently, the translator converts simulation and gameplay logic into a Lua file that can be immediately executed. If the graph defines an object, the Lua file will create a constructor. If the original graph contains an onGraph start, the graph will define what is equivalent to a main function in C++. This will be a member function if the graph defines an object and a static function if not. Extending or modifying translation begins a custom workflow that would generally continue through building and runtime. For example, translating graphs to C++ would involve adding a new translator that produces the gameplay logic in C++ code, building in the compiled results into the O3D project executable, and then calling those functions rather than their Lua counterparts. The next step is building, where the parser and translation results, execution requirements, and implementation requirements are translated into the runtime asset, editor properties, and host environment requirements. When the asset processor and the prefab compiler operate, they both analyze the results of parsed graphs and determine what data needs to be included by the hosting engine to properly execute the logic at runtime. In the case of the prefab compiler, this includes converting some variables in the abstract code model into properties exposed on the ScriptCanvas editor component. In the case of the asset processor, this means generating the ScriptCanvas runtime asset. This asset specifies all the dependency requirements, inputs for static initialization, and for the functions that the entity component system will call at runtime, either the constructor, the main function, or both. These inputs are generally variables that were initialized as editor properties. That is, the ScriptCanvas author specified variables that other users can or must override, for example, entity references. Almost all entity reference values must be passed into the implementation at runtime, and the building step tells the host environment which entities the graph needs to know about. All extension at the build step is by nature custom functionality. At runtime, the host environment, asset requirements, and implementation are finally integrated into functionality. The runtime component will load the runtime asset when it is created. When the runtime assets are loaded for the first time, any required static initialization for the script will occur. When the owning entity activates the runtime component, it will request an execution state from the ScriptCanvas runtime, which will deliver the appropriate one based on the characteristics of the runtime asset. From there, all execution of the ScriptCanvas logic is deferred to the execution state. It calls a constructor if the implementation defined one, and when the owning entity itself activates, the execution state will call the main function if defined by an onGraph start node in the graph. Either way, the user functionality is now integrated into the gameplay. In general, there's no reason to extend or modify the runtime component. However, developers will be required to make new subclasses of execution state for new implementation targets. Thank you very much for watching the lightning talk. I know we covered a lot of stuff very quickly. With this information, you have enough to get started if you're interested in digging into the ScriptCanvas pipeline. If you have more questions or want more details, you can find me on Discord in the SIG content channel under the name Carlito at Amazon. I'm really excited to see the community get involved.